Hi, everybody. Welcome to today's Power Corner. I'm your host, Alia Shokat, Editor-in-Chief, Power Electronics News. Today, we have the pleasure of speaking with Ga₂O₃, Überreiter, VP of Semiconductor Strategy at von Ardenne. Ga₂O, how are you doing today?
Very good, thank you. Thank you for the opportunity to talk here.
Oh, thank you for joining me. I really appreciate it. So I'm going to do just a bit of a quick introduction. You know, I did a little bit of research about von Ardenne. So from what I understand, it's a German vacuum coating equipment company that, despite having 1,000 plus systems operating in 50 plus countries, is still a family business run by Pia
Yes.
von Ardenne. And from what I understand, within the semiconductor space, von Ardenne focuses specifically on physical vapor deposition, so PVD. So the company makes deposition equipment that goes into MEMS, piezo MEMS, and advanced packaging. Advanced packaging, which, for example, integrates power semiconductors with logic chips. And I understand that von Ardenne researchers are actively developing thin film gallium oxide growth methods tailored for device fabrication. So maybe we can first start off with gallium oxide as a semiconductor.
Sure.
You know, what are its benefits and what makes it a compelling candidate for high voltage power devices beyond 1 kilovolt?
Yeah, I think one of the interesting aspects of wide band gaps is that you are actually looking for wider and wider band gaps to be able to switch higher and higher voltages, right? So we have silicon carbide today, we have gallium nitride today. Silicon carbide actually works in a similar voltage range, but there are multiple benefits on gallium oxide that we can talk about later. But the industry is looking for better and better power semiconductors, simply driven by, I think, the growing importance of power conversion and efficient power conversion. Initially, we talked about silicon carbide and gallium nitride in a lot of like electrification of vehicles.
Yes, yeah.
And over the last, I would say, 2-3 years with the AI explosion, suddenly everybody also looks at the megawatt data center kind of contributions. And if you have in the back of your mind that 20-25% of the energy is lost just by going from the generation actually through all of the distribution until it reaches the actual CPU, there's a lot of energy saving potential if we make better and more efficient power semiconductors, and gallium oxide is one way of doing it. As every material, it comes with a lot of benefits, also comes with a couple of downsides that we can talk about. But overall, I think it's a very interesting material that is still, I think, in a little bit of an early stage, but is basically promising a lot of advances from an efficiency perspective and also from a cost perspective.
Yeah. So, you know, as you were saying, gallium oxide's been studied for decades, right? And you know, what changed in deposition technology that makes it viable for power device manufacturing today?
Yeah, I think it's sometimes this like demand and supply kind of dilemma, right? If you're too early and there is not enough demand and people are happy with what they have, it's not picking up. But I think there are multiple things that have changed. One is there is a lot of pull, as I said, right? The second is I think we have now developed methods to create gallium oxide that are much more reliable and much more proficient to generate the material in a way that it's actually relevant for making power semiconductors out of it. And on top of that, I think also in general, the thin film technologies is now progressed enough that you can also make very detailed and very fine layers on top of the actual substrate, because it's not just the material itself, it's how you are actually using it. And that's where I think von Ardenne in particular, coming from a lot of different materials and a lot of different ways of depositing them, that's where we see like the time is ready for utilizing PVD more on those kind of applications as well. And I think it's, as I said, there is a lot of pull, right? EVs, the grid conversion. So all of those things are coming together. And I think it's also the point where there could be another small revolution, I would say, on the power semiconductors.
Maybe we could talk a little bit about that substrate growth technology that von Ardenne's working on, and describe the advantage of gallium oxide versus silicon carbide or GaN in terms of substrate growth
Yeah.
scalability.
It's actually when I joined von Ardenne just a couple of years ago, I was always amazed by how they are using the materials, right? I mean, it's not, they are using certain materials already for years that just now make their way into semiconductors. And PVD is in general a very cost-efficient way of depositing materials. And that's actually one of the downsides of silicon carbide and GaN, right? Making those wafers is still very, very expensive. It's relatively hard to make them on large substrates. So going into 300 millimeter, the industry has been fighting very, very hard to get silicon carbide on 300 millimeter. We're slowly getting there, right? On all sides of the globe. But still, it's a very, very expensive approach, very time consuming, and also a lot of energy consuming. And that's where I think PVD technologies can make a difference, not only in adding layers on top of a substrate, but one of the technologies that we are currently developing is actually also growing the material in the specific crystallographic structure with PVD technologies, right? So it's not just putting layers on top, it's actually also building the substrate itself in a PVD flow, which is kind of novel. And it's even more cost effective then, right? Because you can actually stay in the same tool set.
So just as an example, just let me know if I'm missing something here. I know that GaN needs to be grown on specific silicon wafers, right?
Right.
Is it kind of like that in that you as you were saying, that's not necessary. You can match the structure as you grow gallium oxide?
Well, our technology is able to basically create particular crystallographic structures like atom layer by atom layer, right? So we have a tool that is actually able to grow, and you can tune the process setup in a way that you can get the physical parameters, and with that also the electrical parameters that you want to have. GaN is, when you look at GaN structures, in many cases, it's not just GaN, right? It's GaN, and then it's a little bit of doped here, and then it's another GaN layer, and then it's gallium doped with aluminum. So there's a lot of mixes of stacks. The fundamentals is always, how do you build the base layer, right? And we believe we can do both. While in GaN, you need to basically have MOCVD kind of processes to build the actual substrates. So that's where we believe we actually have an edge of saying, utilizing an element that we use for a long time already and deploying a couple of tricks on the PVD side to basically generate the base layer, but also the layer stacks on top that are required because of some of the deficiencies that gallium oxide has as a material.
Okay. And maybe we could talk about gallium oxides, a little bit more about gallium oxide's appeal for commercial adoption. From what I've researched, P-type doping has been a longstanding challenge in gallium oxide full device integration. So, creating those PN structures needed for diodes and transistors. Does von Arden's deposition approach have any role in solving the P-type challenge, or is that a separate problem that needs to be solved upstream?
Well, I think it's actually it's material inherent, not the way you make the material, right? So that you cannot make P-type doping, or that it's very hard and actually very inefficient and therefore not actually desirable, is something that we will not change whatever method we are using in making the material. But what that drives is a lot of innovation on how you actually build devices on top of that layer, right? Either with Schottky-like devices or with MOSFET. The industry is typically then going into the third dimension and building layers on top and building devices in a different way than just basically embedding them in the actual gallium oxide. So that's what we have seen on other approaches as well. And GaN is not from a P-type doping, but from a device architecture very similar, that there are a lot of, I would say, vertical devices on a GaN film. And that's what we see in gallium oxide as well, right? Overcoming that material challenge, so to say, with other device architectures.
It's interesting. Do you mind talking a little bit more about those other alternative device architectures, for example, with gallium oxide?
Well, if you want to build like other devices, you basically start again adding layers on top with different materials or differently doped materials. And what's then super important is the interfaces of those layers, right? So how exactly does the let's say in the gallium nitride case, how exactly does gallium nitride and aluminum gallium nitride interact on the interface and get a very, very clear and clear surface that you can very nicely tune the device parameters. And that's what we will see on gallium oxide as well, right? Devices that basically go vertical, and you have those junctions that you need to have like on top of each other instead of left and right of each other. And I think that's what the industry is adopting more and more, also to optimize on silicon carbide and gallium nitride. So the same kind of methodology can be used when you basically go to gallium oxide. What will be important is to say we can very nicely create the surface. We can very nicely and very precisely deposit the next layers, and those will be very thin layers again on top, and again have a nice surface and a nice interface. And with those like alternating layer stacks, you can create devices as well that then are utilizing the gallium oxide capabilities of the wide bandgap and the high electric field that you can utilize it for.
Thank you. And we could talk a little bit more about the PVD techniques and the benefits of that. The magnetron sputtering or pulse laser deposition. How does that compare to, say, metal organic chemical vapor deposition or hydride vapor phase epitaxy in terms of film quality, scalability, and cost?
Well, I think in general, PVD is very cost effective, right? I mean, it's much cheaper, it's much faster. And if you think about some of our tools that are basically generating dozens of wafers in parallel as they are spinning in the tool and as we are depositing atomic layer by atomic layer at high speed, you can see how that creates a cost advantage overall for making those wafers. And as we are not limited by wafer diameter, we can basically go as large as we can get substrates to grow things on. That's actually another advantage that plays into that cost. Also, the interfaces that I mentioned, right, making clear surfaces, making them very smooth and very homogeneous is something that PVD clearly does better than CVD technologies or similar technologies. What we have to, and that's kind of the engineering effort on our side, is making sure that the crystal structure is exactly as we want it to be. I think that's where the engineering excellence and the material science come into play on PVD, because that's for a long time has been pushing applications into those more expensive depositioning technologies. But we believe we have some very good engineers who know how to mix the concrete, so to say. And that's where I think PVD will get a much, much bigger role in power semiconductors because of the progress that the engineers have made to make materials and surfaces.
That's very interesting. This is personal curiosity. Have you created any sort of power devices thus far with the gallium oxide technology that you've been working on?
No, we're still in this phase where we're depositing films. We have actually very successfully created what I would call alternating stack films, and not in a way that we move a wafer into the next chamber and remove it and we keep moving it. We basically have a tool where it just rotates, and every rotation it gets a certain like depositing of materials. And as you rotate, you can change the composition of those materials, right? So you can actually you keep the flywheel running. And as it runs over time, you build first layer A, then layer B, then layer A again, then layer B, and you can mix them very nicely in a very fast way. And that's where we're seeing a lot of interest right now, where people say, that's actually how I can make my devices much faster with very different materials.
It's very interesting. What application and whatever you can't reveal, I understand. What sort of first applications spaces are showing interest in this?
Well, I mean, as I said, gallium oxide is the one that we are pushing at, but the same tools are basically able to like gallium nitride and mixes of layer stacks, and that's just the power electronics side. You can also use it for like MEMS applications, right? To grow particular layer stacks or materials to a very thick stack in a very short time. It's kind of the same tools. And that's where we are actually further ahead on the MEMS side. But basically the same physics and chemistry applies when you go into gallium oxide, gallium nitride, or any of those materials. I think what you mentioned before, right? Then you keep going on ultra wide bandgap then with boron nitride and at the end diamond materials. But it's basically a similar kind of problem that you need to solve, right? Getting the right crystal structure and getting it very homogeneously grown very fast. And so we believe with the tools that we have at hand, we can actually switch materials and with that also switch electrical and physical parameters of those materials.
Fascinating. Is there anything that, any comments you wanted to add, any questions that I might have missed? Because you've answered quite a lot of my questions.
Well, I think it's like the cautionary statement, right? I mean, where is gallium oxide from a deployment perspective? Because this is not high volume or like production today, right? I think we're still in a phase where a lot of the power semiconductor players are deploying their next generation silicon carbide factories, even for high volume, right? Where we are seeing a lot of progress in gallium nitride and like multiple variants of gallium nitride based semiconductors. I think gallium oxide still takes a couple of years to get out of that, I would say, experimental phase, and this phase where out of the materials, the application engineers can actually build real devices into something which you would call prototyping or first product. So my personal estimation is it's going to take another 5 years until we see the first products. And then probably another 2 years, 3 years after that, before that gets into real high volume production. But honestly, I think we all believe that we need until 2030 to get to a $1 trillion industry. And now the industry says we are at 1.3 trillion in 27, right? So it seems a lot of things are accelerating. And I think that's also to some extent a wake-up call to the traditional power semiconductor houses, because I think the silicon carbide era will be over much sooner than many people think.
Well, thank you. Thank you so much. I really appreciate your time, Ga₂O₃. Thank you. And this has been a fascinating discussion. I'm excited to see where gallium oxide goes and PVD's role in that, and how von Ardenne will grow that technology.
Perfect. I'm fascinated by it too. Thank you.
Thank you.